So, last time we talked about the divergence of a vector field, and if the vector field is defined everywhere, you can ask for any given point in the space that how much is divergence of that field there. And we discussed this divergence as the definition of divergence was that if you want divergence of a vector field at a certain point, then you construct a small volume, so that the given point is inside the volume, and then there will be a closed surface. A volume always has a bounding surface. So, on that surface you calculate this A dot dA on that surface, this closed surface, divide by the volume of this volume delta tau that you have taken here, and then take the limit as this delta tau tends to 0, all the time keeping that particular point inside. So, shrink this volume, but always keep that point inside where you need that divergence. So, this was our definition, and we told that divergence of the magnetic field, if our vector field is this magnetic field, then this turns out to be 0 for all kinds of current distributions, or any way, in whatever way you produce this magnetic field, the divergence at every point will be 0. So, that is the property of a magnetic field. Now, from this definition a beautiful theorem comes out, and that is, if you have a volume, any kind of volume, any volume, small, big, any volume tau, and then you have the surface of that volume, then from here you can write it as A dot dA on this closed surface. On this closed surface, it is not necessarily small, here it was small, and this quantity will be equal to integration of divergence A, and this is d tau here. So, now you have a finite size, not infinitesimally small, but you have a sizable volume, and so on that volume, in that volume also you can ask that, okay, I take small d tau inside that volume, and at each such d tau you ask, if you take your d tau somewhere here, let us say if you take your d tau here at this point, then at this point how much is the divergence of A, and that multiplied by this volume, and then you add for all the points in the volume, integrate. So, that is the right hand side, and left hand side is you only look at the surface, of this volume, the outer surface, and on that surface you construct this A dot dA, and then integrate over the entire closed surface. So, this is that closed surface, this is a surface integration, and this is a volume integration. This is integration over a volume where you take d tau inside this starting volume that you had taken, and here you take dA, the surface of that, and these two are always equal. And this theorem is known as Gauss divergence theorem. Okay, for magnetic field, since divergence of B is always 0, the only thing that you can derive from here for magnetic field is that the surface integration B dot dA on any closed surface, this is dA, so it is surface must be 0. This is also known as flux of the vector field across or through that closed surface. So, the flux of magnetic field through any closed surface is always 0. That information you can derive from this. Now, the other characteristic property of a vector field can be obtained by defining another vector operation, and that we call curl. This was divergence. This was divergence of A defined this way, at a point, and we define another characteristic property or quantity which is known as curl of vector A at a point. Now, the divergence was a scalar. This was a scalar because it was A vector, dA vector, and then the scalar product, dot product. So, this whole thing was a scalar, and of course, we know if the coordinates expressions in coordinates are given, then we know how to calculate that. So, those expressions were there. Now, similarly, here you have this curl of A, but this curl of A itself is a vector. We write it in this symbol, this inverted triangle which we call delta, then cross, sign of cross, and then this A. So, this is how if you see this kind of thing, you say curl of A. Many times people put arrow here, but that is not needed. I generally do not do that. How is that defined? First thing, this is a vector quantity. Not only A is vector, but curl of A is also vector, and therefore, we start with a particular component, particular direction is in space. So, suppose you have a direction in a space and you ask what is the component of curl A in this direction. This is, let us say, n cap, the direction here, and then you ask at this point I need curl of A, but then to get that curl of A vector at this point, I first define what is the component of that curl of A in this direction, and this is any arbitrary direction that I have chosen at this point. So, we can write it in symbols. This is curl of A and then the component in n cap direction. This is what we are going to define. So, once we define that, then you can get component in any direction you like, and therefore, you get the full vector. Now, this quantity is, you first construct a closed loop around this point, and this plane of the loop is perpendicular to this given direction, a small loop, and on that loop you construct this quantity A dot dl. What is dl? dl is an element of length on this loop. This is dl, this is dl here, 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 this is dl here. So, you have to put an arrow on this loop. If this direction, if you have this direction given to you and then you want the component in this direction, then there is a fixed rule for putting this arrow. And what is that fixed rule? You look from the side of this n cap, you look from the side of this n cap, and then you have to put the arrow in such a way that if you follow that arrow on the loop, that should be anti-clockwise. So, this is the, you have to do that, not only convention, you have to do that. So, you put the arrow in this way and then ask how much is A dot dl here. This A vector is defined at all points. So, you know what is A vector here, and this is the dl vector. So, do this A dot dl, and then you keep on doing this for this and add. So, let me show you in a more explicit way doing a three-dimensional picturization, and here I have a bottle cap in fact, and this is a circle, this is a circle, here is an area, here is an area. A direction is given, here is a point, and this is my n cap direction, this is my n cap direction, and then perpendicular to this direction, to this given direction, I am constructing a loop, and this is that loop, this circle is that loop, this circle is that loop, perpendicular to the given direction. I need component of curl of A in this direction, and therefore, perpendicular to that, in that perpendicular plane I am constructing this loop here, this way, and I have to put an arrow. So, if I see from this direction, the n cap is coming towards me, it is vertically upward in this demonstration. So, this is my n cap direction, I have to look through that n cap direction, my eye should be above that. So, if I see it from here and I have to put the arrow so that the curve goes in anti-clockwise direction, this will be the kind of arrow, this is the kind of arrow. I have to go this way, I have to go this way, I have to go this way, I have to go this way. So, this is how the arrow will be put. If I put the opposite arrow, then I will go in clockwise direction, no, it has to be that. And then at these points, at this point, this is dl, this small small vector in the direction of tangent is dl, and here you ask what is the value of the vector A, and then take the dot product A dot dl, and similarly here, similarly here, similarly here, similarly here, and then you add all those things. So, you get to this closed loop integration, this integration A dot dl here, and then divide by what? Divide by this area enclosed by this plane loop, this area, this whole area. If it is circle, pi times r square. So, delta A, area, not area vector, just this area. So, this, and then take limit, then take limit, then take limit as this delta A goes to 0. So, the size of this loop that shrinks towards this point, original starting point. So, that is the meaning of this delta A going to 0. You shrink it, you make it smaller, 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 and then, but all the time calculate this, all the time divide by this area and take the limit. That is the component of curl of A in this n cap direction. So, if you have x y z axis defined, then it is quite simple. You find what is this curl of A in x direction, curl of A in y direction, and curl of A in z direction, and once the three components are known, you put I cap here, j cap here, k cap here, and add, that will be curl of A. So, this is how we define curl of A at one given point, and that given point can be anywhere in the space. So, at each space point you know capital A vector, and therefore, you also know curl of A vector, you can get it. Now, from here, from this definition, you can get another beautiful relation, and that equation is this A dot dl, integration A dot dl is equal to curl of A, integration of curl of A, and then dot dA dot dA. Just explain what I am writing. Now, what is this? This is, you start with a loop, a closed loop. You start with a closed loop, any loop, in the plane it will be easier. So, a plane loop, let us say, and then you put an arrow. You put an arrow on the loop, your choice, whichever way, this way or that way, your choice. Put this arrow, but once you have put the arrow, then the direction of this dA vector is defined. And what is this dA vector? in this area bounded by this closed loop, take some dA. So, this is the dA. Inside this surface bounded by the chosen closed loop, you take a small area and call it dA, and then make area vector dA vector, and that means this is the area and the direction of this dA vector will be perpendicular to this plane, to this surface, this way or that way. Now, this is not your choice anymore, you have chosen this arrow, and therefore, the dA vector should be such that if you look through that side, dA vector side, then this arrow should give you an anti-clockwise direction. So, in this particular picture, if the area taken, this whole area taken or this loop taken is in the plane of the board, then if I see it from this side, what I find is that it is going anti-clockwise. So, this dA vector will be coming out of the board this way towards me. If I see from here, I find that it is anti-clockwise, that means this dA vector is towards me. If initially I take this area and put the arrow this way, I can put that, no problem, but then if I construct this dA vector and here is that area dA, I have to see from here and I find that it is going in clockwise direction. So, the direction of area vector will be going behind the board, it is going into the board. So, that is how the direction of this dA vector will be determined, and then of course, curl of A at this point where you have constructed this dA. You have constructed this dA in this whole plane, this surface bounded by this curve. So, where you have taken that dA, at that point only you take curl of A, and then take this dot product between curl of A and dA, both are vector quantities. So, this is this side, and what is this side? This side is, you do not have to look what is happening in this area, in the interior area, you only look at the loop itself, the boundary itself, this loop itself, and A dot dl. So, here is dl and there is some A here, so A dot dl, A dot dl, A dot dl, A dot dl, and this way you add, this way you add. So, that is our left hand side, and if you take an area here, see how much is this, an area here, see how much is this, an area here, see how much of this, and add in this for this entire surface, that is the right hand side, and this is equal to this all the time for all kinds of vector fields. All right, and this is known as Stokes law. It's not law, theorem. There is nothing like law here. So, this was Gauss divergence theorem, and this is known as Stokes theorem. And if you calculate what is this quantity, this A dot dl here, curl of A dot dA there for magnetic field, in that case you will find that this curl of B and dot dA, integration of that, this side, curl of vector A dot dA, curl of B. Now, I am talking of magnetic field. And to calculate this B, what is this B now? You have a current distribution, you have some current distribution in the space, and then you know this dB from Bach-Savart law is mu naught divided by 4 pi, and then integration J d tau, that is the current element, and then cross r vector, and that divided by r cube. this is B vector, integration you have taken. So, this is B vector, this is B vector. Your dB vector is, your dB vector was mu naught over 4 pi, then the current element cross R and divided by R cube. And I can remind you what are these quantities. This is in this current distribution itself, you take a small part d tau, this is that d tau in this current distribution, this is that d tau, and see how much is the volume current density here, and then j d tau, that is your current element, and this r is the vector from this chosen d tau to the field point. This is your r. Okay, this is your r. So, and this integration is on this volume. You take this d tau here, you take this d tau here, you take this d tau here, you take this d tau here. This r will keep changing, because if you take the d tau here, then your r vector will be this. So, as you change your d tau, this r vector will keep on changing, and we had this nomenclature. We said that okay, let us have the origin and our frame fixed, and then there is a current distribution. Your current is here and the field point is here. So, field point is here. Then we said that if I take the volume here in the current distribution, this position vector will be called r prime, and this element itself will be called d tau prime. When you change from this volume element to this volume element to this volume element to this volume element, you are actually changing this r prime. And this p here, if you join it from the origin, this we said we will call it r, and in that case this vector from the current element to the p will become r and minus r prime. And then this dB becomes, mu naught over 4 pi, and then j d tau prime, j at r prime, d tau prime, this is your j, and then cross, this is r minus r prime, this vector, and then divided by mod of r minus r prime cube, and this is your dB. And if you want b, you have to integrate this, So, if you want curl of b, what you will do? You will take the curl of this quantity. So, curl of b will be curl of, and b is your mu naught over 4 pi and integration, and then j vector at r prime, this one, and then this d tau prime, or you can write this first, cross r vector minus r prime vector d tau prime, and divided by r minus r prime, and then cube. And you know this curl is differentiation. Okay, I did not give you the expression, let me do it now. We defined this curl, and we defined this curl in some kind of component form. This will be limit and all those things we did. This will be integration a dot dl divided by this area dA, and then limit delta A going to 0 and so on and so forth. But all the time you do not have to do this. If this A is known as a function of coordinates x, y, z, or s, phi, z, or whatever spherical coordinate r, theta, phi, then you have expressions, ready made expressions which are written in the books, and you can use that. For Cartesian, it is easy to remember, and therefore, I also remember. If you need Cartesian, then it is like this: curl of A. If you need curl of A, what you do is you construct a determinant, put I cap here, j cap here, and k cap here. Then del x here, del y here, and del z here, and ax here, and ay here, and az here. So, if you know this A as a function of x, y, z, and what does this mean? That means there are three components, ax, ay, and az, and these components themselves will depend on which point you are calculating this. So, they will be functions of x, y, z. Ax will be function of which point you are looking for this A. Ay will be a function of x, y, z. Az will be a function of a, y, z, and this determinant tells that it is, this determinant is equal to I cap. You write I cap, and then mentally you omit that column containing I cap and column contain the row containing I cap, and then you are left with this. You are left with this, and you write this, then this, you write this, then this, put a minus sign in between. So, del y of Az, del y of Az minus del z of Ay, and then do a cyclic permutation. What is cyclic permutation? I cap will become j cap will become k cap will become I cap, x will become y will become z will become x. That is cyclic permutation, and therefore, plus j cap, I cap becomes j cap, del az, this will be x, z becomes x, y becomes z, so this will be this, minus del ay, so it will be az, and del z, so it will be del x. And one more time cyclic permutation. So, j cap becomes k cap, and then del x becomes y, so this is a y, z becomes x, so it is del x, and then minus here it is this z becomes x, and this x becomes y. Finish. You have all the three components, and the curl of A is ready. So, if you know the vector A in terms of coordinates, you can write such expressions. I do have in the book, I do have expressions in cylindrical and Cartesian in spherical polar coordinates, but when it is needed I will use that. Now, come back here. This curl is essentially differentiations, lots of differentiations. For evaluating the curl, you need all these differentiations, and when you do this differentiation, what is changing? The space point at x, y, z. So, from there you are saying that I need this ax, ay, az here. I know if I go a little bit in x direction, a little bit in y direction, a little bit in z direction, what is happening? So, that is this differentiation. What is changing? The field point where this A is calculated. So, for this differentiation, this is our differentiation. I say that, all right, at this point this is Ax, this is Ay, this is Az, in our case now magnetic field, and then if x changes a little bit, so this is your x, y, z. If x changes a little bit, that means this point is shifting. Y changes del y, so this point is changing, so this r vector itself is changing. So, for this differentiation, remember, for differentiation the unprimed quantities are changing. the differentiations are with respect to the unprimed quantities. You have primed quantities and you have unprimed quantities. This is prime, this is primed, this is unprimed quantity, this is primed quantity. So, you have primed quantity here and unprimed quantities here. For differentiation, what you have to change, when you say delta x, delta y, delta z, you are changing those unprimed quantities. But for integration, this primed quantities are changing. Okay, so this minute point must be remembered, that you have r, you have r prime. If you are doing this integration, then you are changing this r prime, you are taking your detour here, 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 here. But when you are doing the differentiation for curl, then you are changing this field point, it is going here, 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 here. So, that is how it is done. Now, when we are not giving you a particular current distribution, and I am talking of a general current distribution. So, it is a long calculation. In this book we have done that in appendix 4, 5. Yeah, in appendix 5 we have done this derivation of, right, and it has taken full for 1 page, 2 page, 3 page and 4 pages, 4 pages printed pages of book. So, this calculation is really long calculation, but if you go through that calculation and you do that, the result that you find is amazingly simple, and that is this curl of B turns out to be, after doing all this differentiation with respect to the unprimed quantities and integration with respect to the primed quantities over the volume which contains the current, this detour prime. So, over the whole volume of this current distribution, all those calculations you do, and this turns out to be mu naught times j, this j, just mu naught times j. And it is this equation which is known as Ampere's law. It is this law which is known as Ampere's law, and if you use this one, this equation here, then what you can say is curl of B dot dA. So, now you take any loop, and then this is the area bounded, and in this area you have this dA. So, curl of B on this area, will be equal to integration mu naught times j, and then dot that area. Here I am not using anything, I am just putting this integral sign and dot dA on the left hand and integral sign and dot dA on the right hand side. Now, I use this Stokes theorem. For this I use the Stokes theorem. Curl of B dot dA, curl of A dot dA, it is integration of A dot dl. So, this is integration of B dot dl. You already have a loop, you already have an arrow. So, you can calculate how much is B dot dl, and this is equal to mu naught times, what is this? What is this j dot dA? This is the current, total current, through what? Through the area on which you are integrating it, you are adding it. So, for each dA, this j dot dA tells you how much is the current coming out of this surface, and if your arrow is this way, this j direction, positive direction will be coming out of the board, usual from here you see it is anti-clockwise. So, this is the total current which is enclosed inside this area. So, this is another form of Ampere's law, this is integral form of Ampere's law. And this is the one that you have studied in schools, and this is the one that you are studying now. This is the differential form. Of Ampere's law. And this is a point by point relation, remember. At a given point there is a value of curl of B, at a given point you have a value of this volume current density. So, point by point these two should be equal. This is an overall summation B dot dl on a big loop, and then this area integration current through this whole area bounded by the loop. So, this is that kind of an overall quantities, and here it is point by point. And since we are using Bach-Savart law, this is Bach-Savart law, we have committed that we are only talking of steady currents. So, this is valid for, all this is valid for magnetostatics. This is our commitment. If you have time varying quantities, if things are changing with time, then we do not commit, then we do not commit. So, that is about Ampere's law. And once you know curl of a field everywhere and divergence of the field everywhere, and then at boundary of your region of interest, at boundary you know the value of the field, the entire field is uniquely determined. And therefore, curl and divergence are two very characteristic properties, or they contain the characteristics of that field for each point, for every point in that region of interest. So, we will do something from here next lecture.